Okay, I think we can start. Hi, everyone. I'm Hugo Blanco. I'm a software engineer. I work with software for about 10 years. I'm currently a software engineer at Ubiminds, working directly with PowerSchool, that is a multinational ed tech company. I work with assessment teams, and we are focused on delivering assessment applications to a LSM application, that is a learning management system, LMS application, sorry, learning management system. And you can find me on those handles. I don't use Twitter. That's why I mentioned LinkedIn and GitHub. And I was looking for a good scalability definition, and I found this one. So software scalability is an attribute of a tool or a system to increase its capacity and functionalities based on its users' demand. So if we have a high user demand on a tool or a system, it should scale properly. So that's the idea. So scaling software can remain stable while adapting to changes, upgrades, overhauls, and resource reduction. So while scaling a software, we should keep it stable. So that's the idea here. And that leads me to say that your application has a bottleneck, and that's a fact. And I think I can define bottleneck as a situation that stops a process or an activity from progressing. And you will discover that your application has some flaws sooner or later. And the idea here with a plan is to discover that sooner than later and be prepared for what's to come. So for example, your database could be unavailable after a certain number of concurrent users. Your database can have a limit based on its configured infrastructure, or your application server won't handle the amount of memory used to get a large data set. So let's suppose we have to generate a big report, data report for a big customer, and we are not expecting that much data to be exported, to be generated from a report. And that could be a problem for the memory of the server. And that for that large data set, that could be a problem. And also processing delay would be significant for large input or output files. So for that same data report, we can also not expect a lot of rows to be inserted, to be written to a CSV file. So we could have problems reading the data and writing the data, and a lot of other different scenarios we could have. And you will fail eventually. You will. But the idea here is to have a plan to recover and be prepared. So we know we will fail, and we know that we have a bottleneck at some level. So why have a scalability plan? Because we need to understand the points of failure of our application, of our software, and be prepared to them. So having a scalability plan allows your business to remain stable and productive, especially because of the benefits in the long run. There are lower maintenance costs, so we don't have to spend a lot of time working on a fix or making drastic changes we didn't expect. Also, we have higher agility, so having a plan for what to do in case of emergencies will save a lot of time. A lot of time we spent like discussing possible implementations and possible paths to go. And also we have cheaper upgrade expenses. So when we are prepared, I will talk a little bit more in the next slides, next topics. But when you are prepared, when you know what to do in case of emergencies, you can also prevent of having like more expensive costs with upgrades. And the first part of scalability, this is not something academic. It's not there's no consensus about all types of scalability. So it's more based on my experience and more on my the problems I faced. So with resource scalability, we have to understand how many users the system is able to serve with no performance degradation. And how do we scale resources? Just by making resources more resources available to software. just that. So we can scale software, we can scale resources in two types. That is horizontal, that is scaling out. We can scale vertically, that is scaling up. And I will explain the horizontal scaling. So the horizontal scaling is just adding more machines. So I have server A, B, C, and D that are also part of the same, I would say, pool of resources that we have. And instead of scaling up, we are scaling out. So the idea of scaling out is removing the load, removing the demands in a single server. So we have a distributed architecture. And also the horizontal scaling can be configured to be elastic. So for example, we have ELB on Amazon, that is Elastic Load Balancer. And with ELB, we can simply like have more resources or less resources automatically with some predefined configs, depending on the load. So let's suppose I have more load during a certain period of time, and I will add, the ELB will add more service to that pool of resources. And then we can serve more users with the architecture we have. So DLB is good because we know exactly the kind of machine we are expecting to have and how those machines will reduce the demand on the other machines that we had. So we are making the architecture more distributed. We also have vertical scaling. That is scaling by adding more power to the existing machine. So CPU, RAM, disk, so we can add more power to the same machine. But this is the plan where when we don't have a plan. So when we don't think about infrastructure, the infrastructure we are using and how it is implemented, the initial reaction is actually just to add more power to the machine, adding more CPU, and adding more RAM. When we talk about distributed architecture, we're talking about having a cluster. There's some different ways of telling that, but most likely you will find it as clusters. And we have different names for the machines as well, but they could be replicas, nodes, shards, but they are all referring to processing division to have less demand in a single machine. And at some point, this will be the factor that will change the amount of money you have to spend in a machine, because after a certain point, the scaling up a machine that is already powerful, already a robust machine, would cost a lot more than adding a single one more machine. So and it's generally manual. So there's no I know that there are some ways to do that automatically, but it's less common than doing the horizontal automatically. And this scaling comes at a price, of course, because it requires more preparation on the application side. But the benefits go beyond cost of using horizontal scaling. And we also have data scalability. That is how well your data layer responds to additional load coming from the processing layer. So scaling data is a bit more complex. So as your system processing layer scales, so we're talking about, for example, a server with PHP, a server with Java, or any other language that is using that is the processing layer. So as the processing layer scales, more load is placed on the data tier, on the data layer. And it's not about scaling resources, not only scaling resources, but scaling how the data is managed, how the data is read and written. And eventually your database engine will run out of steam and more radical changes are needed. So not only scaling resources, as I said. So even scaling the database horizontally, the application will present a bottleneck at some point, and we need to be more drastic with the changes. We need to understand what are the engines and what are the pros and cons of each engine and how they apply to our architecture, our domain, and our application. And then we go to single node databases. So for single node databases, it's possible to have availability and consistency at the same time, because we have a single node to read data and to write data, and there's no subnet. So a client makes a request and receives a response. We don't have the complexity of having more servers, more nodes. But the thing is, if something goes wrong with the database, you don't have a database, basically. You don't have the data. So the server is not available, and there's no consistency. We don't have the data available, basically. And that leads us to talk about the CAP theorem, that is also named Brewer's theorem. I think I'm telling this correctly, I hope. But this theorem states that it's impossible for a distributed data store to provide all the three guarantees at the same time. So we have consistency, we have availability, and we have partition tolerance. But to talk about the definitions, we first have to understand what is a network partition. That is basically a split between nodes due to a failure of network devices. So when you have a distributed architecture, let's suppose I have server A, B, and C communicating between them, and they are connected by subnets. And if something goes wrong with that, there's a network partition. And part of the CAP theorem is partition tolerance. So it's the ability of a cluster or a distributed architecture to prevent or to remediate those partitions. So we can cause unavailability or inconsistency. And going further in the definitions, we have consistency, that is basically all clients see the same data at the same time, no matter which node they connect to. So going back to the previous one, consistency here would be if I access server A, B, or C, I see the same data. And for availability is any client making a request for data gets a response, even if one or more nodes are down. So in that case, if server A, B, say server A and B are online, but server C is offline, so we can still have server A and B to respond for requests and provide a response. And also partition tolerance is the ability to support that kind of network partition. So the cluster must continue to work despite any number of communication breakdowns between nodes in the system. So when a network partition failure happens, when you have to be tolerant to failures, we have to choose consistency over availability, or availability over consistency. So we have to cancel the operation and thus decrease the availability, but ensure consistency. So how does that work? If I cancel the operation, I'm not making the service available, right? Because I'm denying the request basically, but I'm ensuring consistency because I cannot write to that data, to that data store. So I won't see, for example, server C being the problem because server A and B don't have that data that was on server C. Or we could proceed with the operation and thus provide availability, but risk consistency. So we can't proceed with the operation, but we will have eventual consistency because we will have to replicate the data. And I'll provide some examples, some practical cases. For example, for MongoDB, we have consistency and we have partition tolerance. So MongoDB resolves partitions by maintaining consistency while compromising on availability. So as you can see below, we have a server that is a master. So for MongoDB, we have single master system, and we have a single writer. So when we start writing to a cluster, a MongoDB cluster, the writer is responsible for replicating to the other readers. But the thing is if the writer is offline, if the writer is unavailable, another reader is promoted to writer. And because of that, we don't have the availability as a strong point for MongoDB. We have consistency. So while we are promoting the reader to writer, we don't have the write operations, but we have consistency, right? Because we are not writing until server the first server is back online, or until I have promoted reader to writer. For Cassandra, for example, it's the opposite, because we have availability and partition tolerance. So it's a master layer architecture. Instead of having a single master, we have all nodes as master, basically, or no master. So we have eventual consistency, we have availability. So let's suppose I don't, oh, something's missing here. Yeah, let's suppose I don't have, for example, one of the reader and writer online. I have one of those offline. I can still write and read until the other one is offline, or I don't have to promote any other server to be the writer, because all of those are writers. But I have eventual consistency, because when I write to server A, I have to replicate the data to server B and C. And if I'm writing simultaneously to A, B, and C, it will take some time to replicate to the other nodes, basically. But what about relational databases? So there's an option to use some of those relational databases as single node. So we have availability and consistency, as I said before. And some of those can have clusters, and some engines can sacrifice availability, having eventual consistency. So they use single master architecture, just to provide an example between relational and NoSQL databases. I won't go into details about the choice between relational and NoSQL. I think it depends on your application and what kind of problem you're trying to solve. But it's another important factor since it can impact communication performance, having a multiple node system or a single node system. And then we go to feature scalability. That is how expandable and modifiable the application is without drastic changes. So how do we scale functionality? So laying out a foundation is crucial. So it's good to understand what is the most important thing, what is the most important features for your application. And then you start considering the factors of developing new features. So you start from the foundation and start thinking, what is the work, what is the effort needed to create new features? So we can understand, you can be prepared for new features, but you should not go too far. You can start with an MVP, that is a minimum viable product, and increase the capacity. So you create a good foundation. You start with a good amount of features, important features, a minimum viable product, and then you increase capacity. You understand what could be your features, and then be prepared for them when they come. And also the architecture needs to be flexible. So if you understand that your application, for example, in e-commerce, depends on third party, depends on a lot of different factors, a lot of different libraries, you have to be prepared to have to use an architecture that allows you to expand your features and still be cohesive. And we have code scalability. That is a bit different from feature scalability, because the idea here is to have a larger yet effective code base. Because scaling code is not just writing code that can be understood by machines. You have to write code to be readable for humans as well. Because after all, we write code for humans, right? So clean architecture is something that plays an essential role in scaling. And the code should be well written, should be well documented, because who never looked at their own code from months ago and didn't understood how it worked. So it's totally normal. So we have to write code also for ourselves in of the future, basically. And also be careful with over engineering, because when you start writing too many abstractions and look too much for the future, you could be trying to prevent a problem that you will never have. And some additional tips for scaling: invest in internal testing. So after delivering a feature, or after creating a feature but not delivering directly, invest in internal testing. create doc footing sessions, test internally your code, test internally your ability to grow, your ability to support larger data sets, for example. Also, monitoring is fundamental for scalable systems. And I'll talk a little bit about monitoring the next topic. And cache can be your ally. So you could avoid unnecessary resource requests using cache. So you could avoid making the same queries to the database, getting from a cache. So it's conflicting because cache is still a resource. So you're still making requests to a resource, but you are avoiding making a request to a slow resource in favor of having a faster response, having a predictable response. And using the same idea, we can use memoization. There are higher order functions that caches another function. And higher order function is basically a function that takes a function as argument or returns a function. So if you are calling a function with the same, if the function is deterministic and you're calling a function with the same arguments, you could expect to see the same response without having to make that request again. So we have the result of that function cached. And talking about monitoring, you have to design meaningful metrics. So you have to understand what you should watch, what should monitor. If you need to monitor successes of a third-party API, or if you have to monitor the time taken to process a specific data set. So we have to design meaningful metrics. We have to understand what are the important things to measure in your application, in your domain. And with that, make data-driven decisions. So if you have metrics that are telling you that your code is slow at some point, you have to look at that data and take decisions and prioritize the work on that. Because you could have a bottleneck, you could have a database being slower than expected, you could have less resources than you should have for the processing layer. So it's good to have data to make data-driven decisions. And also for monitoring, it's really important to make sure your infrastructure is operational. So you don't want to be alerted by the customer that your application is not online. You have to understand that beforehand. Okay, but we talked about scaling code, scaling feature, scaling resources, and scaling data. But how can I put together a plan? Where do I start? So consider it early, and when it's most needed, you can grab the benefits in agility. So you can start your application understanding the architecture, understanding everything that I told you. But you could also do that for an existing application. So the idea here is do it as soon as possible because you will need it eventually. You will fail. You will see a bottleneck. You will understand sooner or later that you have flaws in your software. And it's good to understand that sooner than later. And it's good to understand how your user uses your application, interacts with your application. So if you're talking about an application that could have, that could be seasonal, that could have, for example, Black Friday. Black Friday could be, you could receive a lot of users during that time. So you have to be prepared for that. You have to understand how your user will interact with your data, how your user will, the times that the user will be most active. And you have to get, you need to have a good understanding of your data layer and the best infrastructure for it. I didn't go deeper in the NoSQL versus relational, but it's good to understand what works, what is the best fit for your application, your domain. So how that affects your ability to grow. And one thing that is really complicated that is try to predict the growth. So check the usage of similar applications. So unless you're talking about something that is really disruptive, you will see a lot of examples in the market for e-commerce, for learning management systems. You actually you have to check the similar applications. You understand what are the periods where you could expect to see a growth or a peak in usage. So it's good to trying to predict the growth. And it's good to always opt for resources that allow horizontal scaling, because as I said, they are more predictable, they are cheaper, they are more agile to maintain. So it's good to have horizontal scaling. And I think it's even better if you can make it elastic, if you can create predefined configs and make it automatic at some point. It's really good to have a good documentation for the project and gather feedback from all stakeholders. So when you're creating a new software, when you're creating a new application, even a new feature that demands architectural changes, more elaborated, more complex design changes, it's really good to have feedback, because you could think that that would be a problem for a huge high usage, but then an architect, a lead, or senior devs could think differently. So it's really good to have a living document. It's really good to have something to be source of truth after, so you'll understand what were the technical decisions and why the team took them, and also have good runbooks for scaling. So if you understand that for some reason your resources are not that easy to scale, they cannot be scaled automatically, it's really good to have runbooks for scaling, because you communicate to more people how to scale your resource, or maybe how to scale your code, your architecture. So not only for resources, but all the parts interact with your software. But can I predict an unpredictable growth? No, you can't. But it's good to have a good understanding of the flaws and have and know how to overcome them. So you actually know that you will have a growth in a certain period of time, but you don't know exactly how big that would be, or if that would be significant for demanding a real change in the infrastructure. Maybe not, but it's good that you understand how to overcome the flaws, because it's important to be online, right? It's important to have availability, consistency, and you have to grow with being available, of course. And also, prioritization of scalability prepares your project for success. And that's basically it. Questions? No questions.
Thank you, Hugo. It was amazing. So thank you all for being here with us. Thank you. It was very good. It was a pleasure.
Thank you.
Okay. So bye-bye.